Yeah, measurement and units. UME Physics past questions 1983 to 1999. Now, here is a compilation of all the questions from 1983 to 1999 on the measurement and units. So, let's get started. We have UME 1983 question number 29. We've been told of the following derived units, the one that is not a unit of power is. So we need to define what is power. Now, power is defined as the rate at which energy is expended. So you've got power equal to energy or work done per unit time. So what's the unit of energy? The unit of energy is joules, while the unit of time is second. They are SI units. So the first unit you've got is joules per second. So this one is a unit of power. It's a derived unit of power. Now we also know that from electrical energy that power is equal to IV. And the unit of I, which is current, is ampere, and the unit of voltage is volts. So we've got ampere volt. So the second one, B, is also a unit. Now, if you also look at the other formulas for power, you've got power is equal to I square R. If you substitute V equal to IR, and you also try to if you make I the subject formula, if you manipulate this, you get this, and also you're going to be having P is equal to V square over R. So another unit for power is going to be volts square per ohms, because the unit of resistance is ohms. So we know that E is also a unit of power. Now, if we look at this one is going to be ampere square ohms. So you get ampere square ohms, and in here there's nothing like ampere square ohms in here. So and these are pretty much the units of power. If you look at it, unless you want to look at, if you say power is equal to work done per unit time, and you know that the work done is force times the displacement in the direction of the force over time, then the force, you're going to be having force times velocity, which is going to be Newton meter per second. In this case, you're not having something like that. If you having something similar to this. So yeah, we're having two options that don't correlate. We have option C and option D. So rare questions I've seen in a long time whereby you have two options that are correct. So if I were to be in the exam, or I pick either C or D, but if it will be me, I'll pick C, because C stands for correct. So to the next question, UME 1984 question number 7. The unit of quantity of electricity is, now we know that I is equal to Q over T, and quantity of electricity is measured in coulombs. So our answer is the coulombs, option C. And as you can see there, C stands for correct. Anyway, it doesn't only work all the time. Don't always pick C if you don't know the answer to a particular question. But most of the time, if you don't know, just pick C, because that's my own kind of thinking, that C stands for correct. Anyway, that sent me a question number 3. For which of the underlisted quantities is the derived units ml squared t to the negative 2 correct? Moment of a force, work, acceleration. Now, what you see here is is the dimension of a particular quantity. In dimension or in dimensional analysis, we usually think about, or we look at how a particular physical quantity is related to the fundamental physical quantity. Most of the time, the three main fundamental physical quantities, which are mass, length, and time. So let's think about the moment of a force. For the moment of a force, which is also called torque, is going to be force times the perpendicular distance to the line of action of the force. Now, for force is Newton, and we know that force is mass times acceleration, then times distance, and mass is m, capital letter M. Acceleration is meter per square second, then times the distance d. Now we still having m, then meter is length, seconds is time, to the -2 times distance. The dimension for distance is also length, which is represented by L. So we will be having m, L times L, that is going to be L squared t to the -2. So if we compare this to this, we would see that a moment of a force actually has this dimension. And if we look at work is force times the displacement in direction of force. You can generally say force times distance, but if you want to be technical about it, you be force times displacement in the direction of the force. So we've got acceleration, and sorry, before I go into that, force times distance, you can see that force times distance is pretty much the same as this force times distance. So this also has the same unit as this, and you don't even need to think about the dimension of this one, because if we look at the options, there's nothing like three options in here. I mean, the 3 Ohm's figure that are given, we've only got 2 of them here. So all you just gotta do is pick these 2, which is I and II, Ohm's figure 1 and 2. That is option D. UTME 1985 question number 1. Which of the following is not a fundamental SI unit? Now, in physics, we've got 2 main physical quantities. We've got the fundamental quantities, and we've got the derived quantities. Now, for the fundamental quantities, we've got fundamental units, and for the derived quantities, we've got the derived units. Now, in science, we've got 7 main fundamental quantities under the SI system. So, for the 3 main ones are mass, length, and time. And their units, of course, like I said earlier, they're fundamental units. So the units of meter is a fundamental unit. Sorry, the units of length, which is meter, is a fundamental unit. The unit ampere is the SI unit for electric current, which is a fundamental quantity. So ampere is a fundamental unit. Kelvin is the SI fundamental unit for temperature. Second is the SI fundamental unit for time. Radian is not a fundamental unit. Radian is a fundamental quantity. Radian is for angular measurement. The next question, we asked which of the following statements are true about spring balance and chemical balance. Both are used to measure the mass of an object. Nope. Spring is used to measure the weight of an object, while chemical balance is used to measure the mass of an object. Chemical balance or a beam balance. Either of them may be used to measure the weight of an object. Nope, this is wrong. This is also wrong. Woman's figure 3. The spring balance works on the principle of Hooke's law, while the chemical balance works on the principle of moment. I'm pretty sure you must have seen a spring balance before and also a chemical balance. You would know that a spring balance, the main constituent is a spring, which works on the principle of Hooke's law, while the chemical balance works on the principle of moment as its two lever arms. So this is absolutely correct. Now for woman's figure 4, a change in gravity changed the reading of a spring balance. Yes, that's true, but not that of a chemical balance. Yeah, this is absolutely correct, because a change in gravity will change the readings of a spring balance, since the weight is dependent on G, which is acceleration due to gravity, and this is dependent on the place you are. So it will change when you change places. So that implies that the gravity there will change. But for a chemical balance, since the clockwise moment is gonna be equal to the anti-clockwise moment, then the G will cancel out, so the G wouldn't matter. So our correct option is option C. UTME 1986 question number 1. We asked which of the following represent the correct position if the length of a piece of wire is measured with a meter rule. Now, one thing you need to understand is for a meter rule, the smallest graduation is in millimeters. So we have the smallest division, or the least count, is 1 millimeter. Now, the rule of thumb is that for you to estimate further or beyond this division, it's going to be 1/2 of the smallest division, which is going to be 0.5 millimeter. So what this implies is this. Actually, this shows the reading accuracy of a meter rule. So what it implies is this: if I measure a length to be 35 millimeter, since I'm being allowed to go a decimal place beyond the least count, then I will put this as 0.0 millimeter if it's exactly on the 35 millimeter mark, or if it's beyond the 35 millimeter mark, probably it's in the middle of those tick mark. Let's say this is a meter, then you've got, these are the millimeter mark. Let's say the length of something you're measuring falls somewhere around here. It falls in the middle, or closer to this. You might decide to make a judgment of it falls in the middle, that is 35.5 millimeter. I am not allowed to say this is 35.1 millimeter, because your eyes, you wouldn't say your eyes is really that precise to measure it up to that level, or the vision of your eyes is really that good to measure to that kind of division. But you could decide to say, okay, maybe it's 35.3 mm, depending on how you considering things. But based on the rule of thumb, you don't go beyond this. You don't go lesser than this. Rather, you stick to 0.5 mm or 0.0 mm, or 1 millimeter, or half of a millimeter. So in this case, our answer is going to be option B. You can't write 35 mm, because in that case you are not showing that, oh, you can estimate further, since you can only write to either 0 or 5 off the decimal place beyond the least count. So that's for that. Question 4 of the same year. Which of the following is a derived unit? Kilogram is a fundamental unit. Meter is a fundamental unit. Kelvin is a fundamental unit. The unit for temperature. Newton is a derived unit. So our correct answer is option D. As a matter of fact, I should cross this because these are wrong for the answer to this question. So the correct answer to this question is option D. Newton is a derived unit, which is the SI unit for force. UTME 97 question number 1. Which of the following units is equivalent to kilogram meter per second? Now, if you take a good look at it, you will notice that this is the unit for momentum, because momentum is mass times velocity. Mass is in kilogram, velocity is a meter per second. So that is for that. And from impulse, which is Ft equal to change in momentum, they have the same units. The unit for force is Newton, while the unit for time is second. So we have Newton second, which is equivalent to kilogram meter per second. So that is our answer, is option C. UTME 1988 question number 2. Which of the following are the correct SI units of the quantities indicated? Now for Newton, the force is the quantity for Newton. So the Newton is the SI unit for force. This is correct. Newton per meter. No, that is wrong. The unit for torque is Newton meter. So this is absolutely wrong. For watts is the SI unit for power. So this is correct. For momentum, meter per square second. No, this is wrong. The SI unit for momentum is kilogram meter per second. So our correct answer here is option D, 1 and 3. Next question, UTME 1990 question number 1. What is the reading of the vernier scale above? Now, this is a large or a zoom-in view of a reading on a vernier caliper. Now, for a vernier caliper has two scales, the main scale and the vernier scale. Now, what you've got to understand is that each division on the vernier scale is 0.01 cm lesser than each division on the main scale. So I don't want to be pedantic about this, but the way I usually do this is that I just look at the mark on the vernier scale, which coincide with the mark on the main scale, and I multiply it by 0.01. I don't want to go into much details, but just you can always do it like that. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8. So the 8th mark on the vernier scale coincide with this mark on the main scale. So, and that falls on the 8th mark on the vernier scale. So that is going to be 8 times 0.01 centimeter, which is 0.08 centimeter. Then on the main scale, you look at the reading or the mark before the vernier scale comes in. Now, if we look at this is centimeter, and this centimeter, it's also further divided into 10 divisions. So that implies that each division is 0.1. So this is going to be 1.9. This is going to be 1.8. So it implies that this reading before this vernier scale comes in is 1.8 centimeter. And what you now do is you add this to this one here, to the reading on the vernal scale. So that's going to be 1.080 centimeters plus 0.08 centimeters, and we will be having, this is going to be 8.1, so we'll be having 1.88 centimeters, which is option A. That same year, question number 2, which of the following is a fundamental unit? Newton is not a fundamental unit, it's a derived unit. Likewise watts, likewise joules. So the fundamental unit we've got in here is option D. UTME 1992, question number 1. What is the least possible error in using a rule graduated in centimeters? Now, I love this question because they made use of the word rule here. Now, they didn't say meter rule, they said rule. Now, any rule could be graduated in any measurement, but in this case, it is graduated in centimeters. That implies that the smallest division on the rule is 1 centimeter. And based on the rule of thumb, we've got 1/2 of 1 centimeters, which is going to be 0.5 centimeters, and that is going to be option B. UTME 1993, question number 1. Which of the following quantities has the same unit as watts? Now, watt is the unit for power, and we know that power is work done divided by time. Work done is force times displacement over time, and that is going to be force times displacement over time is going to be velocity. So power is still the same thing as force times velocity, which is option D. That same year, question number 2. The external and internal diameters of a tube are measured as 32 plus or minus 2 millimeters and 21 plus or minus 1 millimeter respectively. Determine the percentage error in the thickness of the tube. Now, for us to get the absolute error in the thickness of the tube, now for the thickness, let's get the thickness first. The thickness is going to be 32 plus or minus 2 minus, that's the external minus the internal, 21 plus or minus 1. Now 32 minus 21, that is going to be 11 plus or minus. Now here's where you are very careful. Don't think because you're subtracting the internal diameter from the external diameter that now you're going to be subtracting this error from this error. No, if you really think about it, you're having error in here, you're also having error measuring the internal one. So the total error you will be having is going to be the addition of the two errors. If you really think about it, it makes sense. So 2 plus 1, that is going to be 3. Now we have the absolute error for the thickness of the tube. So if we want to get the percentage error, the percentage error of course is going to be the error divided by the measured value times 100. And if I'm to get my calculator out for this, I have 3 divided by 11, and that is 0.27, then times 100. I believe you can figure that out already. That is going to be 27.2%. So we have 27.2%, which is approximately 27%, and that is option A. UTME 1994, question number 1. Now this is also a linear caliper, and we've got the main reading and the vernier reading. So let's check where they coincide for the vernier reading. So we have ES 5, 6, 7, 8, 9. So that's going to be 0.09 centimeters. Now for the main one, yes, of course, this is going to be 1.4, this is going to be 1.3. 1.3 before this one comes in, so we'll have 1.30 centimeters. If we add this up, we have 93.1, so we have 1.39 centimeters, which is option C. UTME 1995 question number 1. Which of the following is the dimension of pressure? Now we know that pressure is force per unit area, and force is mass times acceleration over mass times acceleration. Then with the pressure now we're having over area, the mass, we have mass is m, capital letter M. Then we are having acceleration. Remember that acceleration is meter per square second divided by area. So we will be having capital letter M. The dimension for meter is length. Dimension for second is time. So we have T, capital letter T, to -2 divided by the dimension for area. If you think about it, area is length times length, which is going to be L to the 2. So we will be having ML T to -2 L to the 2. So which of the following is the dimension of pressure? The dimension of pressure is going to be, okay, we can still simplify for that. That would be ML T, L and L to the 2, that would be L to the 3, T to the -2. So our answer is, oh, sorry. Taking this up is -2, so that is going to be 1 minus 2, which is going to be -1. So that would be M L to the -1, T to the -2, which is going to be option A. So I guess I have to erase this part off so that I'll be able to write here. So here we are told, at what respective values of x, y, and z would the unit of force, the Newton, be dimensionally equivalent to m to the x, l to the y, t to the z? So force, just like we worked here, is going to be m l t to the -2 for force. So that is going to be 1 1 -2. So we have 1 1 -2, option B. So UTME 1998 question number 1. The physical quantity that has the same dimension as impulse, of course you know that impulse, Ft, which is I, is still the same thing as change in momentum, and that is going to be option B. UTME 1999 question number 9. The internal diameter of a small test tube. The internal diameter of a small test tube can be measured accurately using, is it going to be micrometer, screw gauge, a pair of dividers, meter rule, or a pair of vernier caliper? It's going to be a pair of vernier caliper. Of course, you can use a meter rule. A pair of dividers, since it's really small, if you take a pair of divider and you transfer it to a meter rule or to a ruler, you might not really get that precise measurement. A micrometer screw gauge is used to measure external diameters, and besides, we are told a small test tube. No one might think that, okay, I can use a micrometer screw gauge to measure the diameter of a test tube if you want to be really precise, but it's not used for internal measurements. It's only used for external diameter. That is why a micrometer screw gauge wouldn't be the ideal answer. That is for that. Now this is the end of the video. I'm your tutor SB Sanni, and you can follow me on Twitter. If you've got more questions you want to ask me, you can always send me tweets and I'll reply you. And I would also want you to like, share and subscribe, and we'll see you next time.